Welcome back to the garage, guys. Today we got a little bit different video for you. We thought we would take a few minutes and talk about some of the tips and tricks to running these. We're getting a lot of emails recently from a lot of you guys because there's getting to be dozens and dozens and hundreds of these out there. So we thought we'd take a couple minutes and go through a few things that will help you guys out with running your machine. So it's a few best practices, a few tips, a few things we've learned. Now our machine's about a year old and we've been running the heck out of it. I think you saw in the intro some of the sheets we've just hauled into the scrap. So with that, we'll get into the video. So with that, Jackson, what's the number one question you get?
Well, I think the most emails I get are about how to make the Z-axis actually do its thing. Touch off and probe, and how to set your heights and all that. Basically, by the time this video goes live, there'll be another section in the plans about how to actually set all that up to whatever you may be running.
So back to the Z-axis, Jackson. Just give a quick tip for the guy that's just starting out with the Z-axis.
Well, I think setting your cutting heights is actually a really important thing. It'll help you get the best finish. And basically, to set your cutting height, you want to go through half the thickness of your material. Seems to be a pretty good rule of thumb. But if you're cutting, like 24 gauge metal, I wouldn't go any closer than like a millimeter or so.
Okay, that's cutting height. There's also with the Z-axis, we do a separate pierce height. So what do we do for pierce height?
So on the pierce height, I would just double your cutting height. And the reason for this is when you punch through the metal, you're gonna get slag blown up back up to the top, and you want to minimize the chance of that actually hitting the tip. So we typically use it between a 3 and 6 millimeter pierce height, depending on what metal we're using. Just so you gotta be close enough to get through the metal, but you don't want slag pushing back up and potentially ruining the tip. And what would be the number one question that you get?
The number one question I get is, can I make it bigger? That's the first thing. Well, I'd like to start out and say that it's no secret that a lot of this, the look of this machine looks like a Langmuir machine with the cantilevered gantry arm. We're already about 4 or 5 inches longer this way than a Langmuir machine, so we don't recommend making it any bigger that way. If you want to make it bigger this way, go right ahead. And we're going to show a little bit deeper in the video about some accuracy. Guys go, well, what about belts? If they get longer, what happens? So we're going to show something about accuracy further along in the video. Okay, Jackson, what would be your top tips to give to somebody who's just starting out getting their machine set up and running?
So the first thing I would say is know when to change chips on your torch. You're going to know when it comes time to change. You're going to have a lot more sparks coming out the top of your metal. There'll be a lot more of that coming out the top, and when you're starting your pierce into the metal, you'll notice that it'll take longer, and you can hear when it actually goes through, and especially on thicker material, you'll notice that it'll take quite a bit longer. That'll tell you when it's time to change the tips. The second thing I would say is when it comes time to removing slag is just hit it off with a chisel. It's the most efficient, just easiest way to do it. You don't grind it off with a grinder or belt sander, just hit it off with a chisel.
Yeah, and we tend to just drop the piece on the cement floor, and it takes most of the slag off. It's kind of a pain to go sweep it all up, but just dropping it on the floor pops off the slag.
And then the third thing would be having dry air by putting an air separator in your line. And what we have is a water drop from Amazon, and then
Harbor Freight on this one.
Or Harbor Freight on this one, and then this one's a motor guard from Amazon, and we'll have a link in the description of where you can buy these. And
so we go into the water separator first, the Harbor Freight, and then we go into the motor guard. This has like a toilet paper filter in it, and then we go out into the machine.
And by putting this on, we actually gain a lot of tip life. And sometimes you get one drop of water and then your tip would blow out in 5 minutes. And this really, really helped a lot, especially on thicker material. And the reason why we don't have this on now is because we bring it inside when we're not using it, so all the water doesn't freeze inside of it. We can get it drained properly after we use it. So Jeff, what would be the 3 things that you would recommend the folks watching at home?
Well, the first thing I would say is when you're doing creating your tool paths in Fusion, when you're getting ready, that you want to add lead-ins. So the torch starts outside of your cutting path and then moves into the cutting path. Generally speaking, you're going to have to, the thicker the metal, the longer your lead-in is going to be, but it gives you a smoother perimeter on your cut, whether it's a hole, an inside cut, or a perimeter on an outside cut. The second thing is use the appropriate tip size. When I say tip size, I mean the orifice in the tip. We have 0.6 millimeter, 0.8 millimeter, and 1.1 millimeter. That's what we use. We use the 1.1 millimeter for thicker than 1/4 inch. We use the 0.8 millimeter for 1/8 inch to 1/4 inch, and then the 0.6 millimeter for everything lighter than that. And we had someone give us a tip in one of our earlier videos about voltage, or excuse me, amperage, how much amps to run. Well, the 0.6 tip is rated to 30 amps. So no matter what we're cutting with it, we're running at 30 amps. We're running it right to the peg. And when we use the 0.8 tip, it's 40 amp tip, so we run it right to 40 amps. And then the 1.1, we run it right to 55 amps, and that's the max on the Lotus machine. So we run it wide open to up to the tip size. The third tip I would say is be careful when you nest your parts on a cutting job. So we've got a sample back here if Jackson can grab it. So it might be hard to tell on camera, but we did a pretty good job nesting the parts on this. So we got a good efficient use of the metal. But if we look over here, we had a lead-in coming in. And when the torch came to cut the outside, it came around, and as it was coming down, since it was such a small lead-in, it broke off and the metal moved and cut this part out wrong because we had such a small space between here. So I would say when you're nesting your parts, leave yourself a little bit of room. You know, 1/4 inch is a nice amount, something like up in here. These were too small. We got efficient use of the metal, but if you room apart, how efficient was your metal? So those are the 3 tips that I would say for guys starting out.
And then when you go with nesting, that kind of goes back to the knowing how small you can cut based on how thick your metal is. So you can't ever have a dimension under the thickness of your metal. So if these are if this is 1/8 inch metal, you can't ever have anything under 1/8 inch, or you're gonna run into problems. We would recommend actually just doubling that, just to play it safe.
The other thing, when this was cut, if we look at these long skinny pieces, they were set on the slats like this, so they fall through. So they fall down into the water pan. Before we were cutting them like this, and the slat would sit underneath and we'd get a tip up, it ruined the whole job. So if you look at this job, everything that's narrower than the slat width, we've got running this way. If it's wider than the slats width, we ran them this way so they sit on 2 slats and they don't fall through. Everything else falls through. It's really limited our tip ups and failures on jobs. So one other thing with our slats here that we've done is when we set these slat heights in here, we set them so they're at least even, if not maybe higher than the edge of the water pan. In our case, they're completely even, so we can set on a bigger piece of metal and cut it. We tend to buy metal in 2x4 sheets, and we can set that sheet across here and just have the plasma cut it into a 2x2. Or sometimes we'll let it overhang and just feed it in as we're working. But so important to have your slats at least as high as your water pan or higher. Don't make them lower because then you're going to be stuck moving metal around. The other thing on slats is we have 1, 2, 3, 4, 5, 6, 8 slats. If we had 10 or 12 slats in there, we would have probably never had a tip up.
Yeah, it'd have been a lot better. We just We just happen to not pick the right amount of slats in the relation to probably the average size part we're cutting. So we'd either have to remove 2 or go up 2, and I would prefer to go up 2.
Yeah.
2 slats, because you almost can't have too many, but if you have too little, you're gonna run into problems.
And 2 or 3 more slats is gonna cost us another $5 or $6.
Yeah.
You know, and so when it's time to remake these, we flip them over, they're getting wore out. When it's time to remake them, we'll put a few more in here. So Jackson, I've had some discussion with some people that are adamant they want to put limit switches on this machine. I try to explain to them that they're not necessary, but maybe you want to have a go at your opinion of limit switches.
Yeah, I wouldn't add limit switches on something like a 3D printer. Yeah, they're necessary, but on this, absolutely not. I wouldn't put them in. And the reason is, if I were to have a limit switch and send it to home, well, home is, if I have limit switches, ends up being way up in this corner out here. Well, I don't really want to cut on the end of the pan, so I'm going to put my sheet somewhat in the middle, and my 0 point for the job's on the corner of the sheet. So I'm just going to jog the head till I'm reasonably close and just set it to home.
So if you had a limit switch here, you'd actually have to program a offset where the torch was going to start cutting, and then you'd have to locate a pan, or you locate your metal to that location for your limit switch to work anyway.
Yeah, you'd have to program a work offset into there, and then you'd have to have your sheet in the exact same spot every time. And I don't know about you guys, but I don't want to put that much work in when there's an easier way to do it.
So how do we ensure that we never go to the end of the movement? So what's our procedure when we're drawing out our parts?
Oh, so when I'm nesting parts, I'll just draw the stock in Fusion. We normally use 2x2 sheets for everything, and I'll just draw a 2x2 box in the program and just drop all the parts in there. And that way I know I'm getting the most I can out of the sheet without wasting, with as little waste as I can. And it doesn't really matter, I might be 2 or 3 inches off when I just throw it on there. It doesn't really matter as long as it's square. It'll work.
And the other thing, if we've got a piece of 1/4 inch 2x2 feet and we just want to cut a small part out, he still draws the box, we cut the part out, we save that file, so the next time we have 1/4 inch, we just pull it up and we know what parts of the sheets have already been used and we put it in. So as long as you draw your part inside the 2x2 window, or in this case the 28 by 30 inch window for the water pan, you'll never be outside of the cutting range. You'll never hit an extreme limit. And if you do hit the end, if it goes down and hits the end, it's no big deal. We're going to show that later on in the video too, how you can run these down to the end. We hit them all the time when we're not paying attention. Not during a cut job. The other thing with a limit switch, if you were to ever hit a limit switch during a cut job, your whole job is ruined at that point. So everything you've done is waste up until that point. So we're not a big fan of them on a table like this. There's no need. What's the second reason you wouldn't put them on?
Well, this is in case the extreme unlikelihood that would actually happen. We're running 6 more cable or 4 more cables, and you may have interference, and let's say a hard limit thinks it's tripped in the middle of your job. Well, worst case you got to restart the job, or best case you have to restart, and worst case you just ruined your whole sheet. So Dad, it was your idea to build this table, and after about a year of working with it, is there anything that you think we should do differently or change on it?
Well, one of the things that we definitely messed up on, it's a terrible oversight, and I hope people, and I'm sure people are doing the same thing as we did. We should have changed it. We should have something in the instructions, but we have our control box for all the electronics right here. Every cut job we do, our starting point of our X and our Y is right there. So all the water, all the dust, everything that flies all around lands on our box. There's almost no cutting up in this car, very little cutting. So if the box would have been way over here, it'd have less stuff getting on it. Now, we haven't had any trouble. We haven't had any shorts, anything like that, but it's, you know, we do keep a towel on it once in a while if we're coming back to home a whole bunch in a big job with that. The other thing, this thing being a year old, the other thing that surprised us with this machine is the durability of the 3D printed parts. This thing has had no maintenance. We haven't done anything to it. Today when we were getting ready to shoot the video, I did a little bit of wipe down and we had it out in the sun to melt the ice off it. There was ice all over the thing, and I started looking down into it, and on a couple of these bearing blocks where the set screws go, there's no set screws in them. And when I saw that, I go, oh crap, you know what? I was always gonna buy those set screws. We didn't have enough when we put it together. So some of our bearing blocks don't even have all the set screws in it. And the thing's been running fantastic. You know, the gantry arm has no play in it. It's just been as robust as we could do. The other thing, we shot a few videos in this series, and about somewhere between the second, third, or fourth one.
Between the third and the fourth.
Third one, we kind of redesigned the bearing blocks that went on, and these are actually, we consider them today reject parts. These aren't even parts we would produce for ourselves or send out.
Yeah.
It's a little different design. It's not as thick, not as heavy, and again, it's a year later, and there's just no wiggle on that thing. You know, I can move it this way. It's plugged in, excuse me. So, can't move it that way now with it being plugged in, but it's rigid, the design's held up. Maybe, you know, just recently we've been looking at it because we froze up a couple times, but we probably put a splash guard on the Z-axis. But I don't think there's many guys that are gonna be out running their plasma cutter at 0 degrees or 10 below. You know, we're kind of glutton for punishments. And again, it's cold again today. It's 10 degrees. That's Fahrenheit, not Celsius, guys, so it's cold. So Jackson, you do all the post-processing on this once the parts are drawn to get them ready to send to the machine. So as far as speed, what kind of speeds are we using for like 1/8 inch and 1/4 inch?
So on 1/8 inch, we're cutting at 2200 millimeters a second, or millimeters a minute. And how we arrived on that is, this goes back to the tips. You're gonna wanna just run the max amp for the tip, and then you're gonna just take a couple of passes. You've seen us do that in other videos. So you just take a couple of passes at different speeds, and then you're gonna look at the cross section of the metal. And you're gonna see some lines on the metal that are lagging behind the tip, and you want them to be anywhere between like 15 and 25 degrees. And that's how you tell when you're getting the basically the perfect cut. And you can also just flip the metal over and just pick the one that has the least amount of slag on it.
Yeah. So on the edge of the metal, you'll see a little, your lines will be like this. Now Jackson, what happens if you cut out a hole when you're running that? Now, if you slow that down, that kerf angle will stand up straighter. So what do we do when we cut holes?
Yeah, so we actually slow our holes down by 40% up until about 1 inch. Once the holes get to about 1 inch, you don't really have to do that anymore. But the bottom of the arc, or the flame, is slightly lagging behind, and what happens is when you cut that hole and you go around in a tight enough circle, it creates like a funnel, pretty much. And if you slow that down, it lets the arc catch up, and then it'll keep things nice and square. Now, you don't want to do that when you're cutting regular, because you do produce more slag and your overall job just takes longer. But for holes, it actually helps a lot.
So Jackson, with the guy just got done assembling this, he's got the motion tested out, he's got his parts post-processed, and he's gonna do his first cut. What's the biggest piece of advice you could give him?
You have to square your torch. You have to make sure your torch is square or perpendicular to the piece of metal you're cutting. If you don't do that, you're gonna have a weird bevel on your entire part, and it's all gonna be pointed in the same direction. So it's gonna look really bad, and your part's not gonna turn out right. And I'd actually recommend that you just don't use the Z-axis for your first few cuts. You just manually set the torch height and make sure that it is actually square.
And a lot of times, before we had the Z-axis, we set, you see people using jigs and doing measurement. We just use playing cards, somewhere between 4 and 6 playing cards to slide under the torch tip. That's what we used forever. And the squaring of the torch is done with the set screws on the Z-axis, or excuse me, on the X-axis here. So I think they're in the we have the instructions to tell you how to do that, but it's important to make sure that that torch is plumb to the metal. So one of the things we hear about, or we see on message boards, and we see comments in the video, what's the accuracy of this machine? Well, I want to talk first about the torch and the kerf or the arc of the torch. So I don't know, I'm no artist here, but if we have a torch, this is my torch, and this is where the arc comes out. The arc comes out and it's egg shaped like that. So it has a lot to do with where your metal's placed. So you want your metal placed, where the arc is the flattest. If you have your metal way up here, you're going to have a big kerf angle. And if you have your metal in the middle, that's the optimum spot. So when we're using a 0.6 tip, the apex of the arc is up higher. When you're using a 1.1, it's way down lower. So like Jackson said, the good rule of thumb is half the metal thickness for torch height. So your kerf profile has a lot more to do with the accuracy of your cut than the accuracy of this machine. And we're going to show you what the accuracy of this machine can do.
And one more thing is the smaller your tip, obviously the smaller your kerf is going to be, but the ability for leeway is going to be a lot smaller.
Yeah.
So you're going to be taking less metal out, you can cut faster, but your torch height is a lot more critical.
And that's another thing in fusion. If you set up your tool heads, we have a different profile for 0.6, 0.8, and 1.1. So we have a different distance set in there for that kerf width, so that the program knows how much to compensate to get us a final part that's dimensionally correct. So in order to test the accuracy of our machine, we came up with a method. So what we've done is we've mounted a dial indicator on the gantry arm, and we have it way out here on the outside of the arm. And if we can look at it, we're just a hair over 0. See if I can't get that back to 0. Right there. And now we've got a cut job that we've got loaded in the machine. So it's from the crosscart spool that we sell. So we're going to go ahead and cut this job. We're not going to use the torch on it. There's no reason to use the torch. We don't want to put water in it and have to deal with the ice and stuff, but we're gonna run this cut job, and then we're gonna take it back to home and see what happens, how accurate we are with the dial indicator on the gantry arm. Okay, go ahead, Jackson. Okay, it looks like the cut job's done, guys. We're going to take it back to the home location and see how we did on that dial indicator. So there you go, guys. I don't know if you're getting a good look at it. I'll take the phone out, the holder, but that's accuracy. So we've got the dial indicator set up now on the X-axis. We're not going to run the job, because if we run the job the way we had to set the dial indicator, it'll get knocked off the base. So Jackson's just going to manually move it around. So go ahead, Jackson, move the X and the Y, and we'll move it around. Okay, I think that's good enough. Jackson, just take her back to the home position. I don't know what you guys think, but that dial indicator is about dead on. I mean, maybe another half a thou out. I don't know. Accuracy of this machine's fantastic. It's more about how you have your kerf set up and your squareness on your torch. Just got to pay attention to the details, guys. We appreciate you watching the video. Thanks for sticking around to the end.